So welcome everyone to the discussion of a new data structure, graph data structure, and we'll be talking about graph abstract data structure. So we are not going to talk about the implementation details or how programming languages implement this. Rather, we are going to talk about the features and operations on graph data structure. So far we have talked about different linear data structures, if you remember, like so some of these linear data structures were like arrays, right? And then we talked about linked list. If you have missed this, please go back and watch the videos on these data structures, because throughout the course, you will come back and you'll keep on needing these. So you cannot just skip and go ahead and solve the problems. If you haven't watched this, please watch them back. Or if you have forgotten, please take your time to watch them back. So these are the linear data structures that we discussed, right? And then we also talked about hierarchical data structure or hierarchical data structure. So hierarchical data structure, we talked about tree, right? Okay. So today we're going to talk about a non-linear, not a linear data structure. We're talking about a non-linear data structure, that is graph. Okay. So what is a graph? So graph is a collection of entities known as nodes or vertices. So nodes or vertices, collection of entities uh, known as nodes and vertices, and these nodes are connected to each other through edges. So as you can see from the diagram here, or from the picture here, A, B, C, D, E, these are the nodes and vertices, and the lines that are connecting them, those are edges. Okay. So once we are talking about nodes and vertices and edges, probably this is ringing some bell, right? Because already we know about a tree data structure, right? So if you remember, in a tree, we also have these nodes and vertices, right? And we also have, say, edges. We have these edges, right? So the question is like, then is tree a graph? Yes, tree is also a graph, but the tree has some constraints. So the constraints is, in a tree, all the edges actually define a parent-child relationship. So suppose this edge defines that I is a child of D, okay? Child of D. So in a tree, all edges define a parent-child relationship. But, and also in a tree, you cannot have, say, you cannot have something like this, right? You cannot have something like this, because every edge has to have a, say, a relation. It defines a relation. So here you see that C is a descendant of A, right? Or D is also a descendant of A. So from a tree perspective, D and C are, say, siblings, right? We talked about siblings. So these two are siblings. But if you have a, like, try to add an edge here, then what happens? Then the relation becomes complicated, because these two, what are they now? Like, are they parent child or siblings, right? So that's the constraint. So you cannot have something like this, right? There is a formal term for something like this, so we will talk about that later. But in a tree, every edge defines a parent-child relationship. That's important. So tree is also a kind of graph, but that's actually a subset of graph. So among all types of graphs, tree is one kind. So as I said, graph is a collection of vertices and edges. but there is no constraint in a graph. So you can have, you see that any edge can be, sorry, any vertex can be connected to any other vertex. That's what a graph is. So there is no rules on the edges and other stuff on the edges. Okay, so how do we define a graph? So we define a graph like this: G equals to V and E. So V is the set of vertices and E is the set of edges. Okay, so here say V is, in this graph, V is going to be A, B, C, D, E. So these are the vertices, right? And what about E? E is the set of edges, right? So let's say we name every edge. So we say like this is E1. Okay, sorry. Okay, so this is E1, this is E2. So we can say that E1 is actually this, right? Okay, so so we can say that each of these edges, AB is a edge, right? And then AC is another edge, right? So these are all the edges. So basically, we are defining each edge as a pair of vertices, okay? So this is how we define a graph, as a set of vertices and edges, where each edge is a pair of vertices. Now, the thing is, the graph that you are seeing here in this diagram or in this figure, you see the edges don't have any direction. So between A and B, there is an edge, right? But there is no direction. So this is called an undirected graph. So this is an example of an undirected graph. See, if nothing is told, like if it's not explicitly told, then any graph is an undirected graph. But obviously we can have directed graph. So here is an example of a directed graph. So directed graph is, we see the vertices and then there are edges, but these edges have a particular direction. Okay, so you see between B and C, there is a directed edge, right? Okay. So between B and C, there is a directed edge, and then between, and obviously, it's possible to, since it's directed now, right? So there can be edges in both directions. So say from C to E, there is edge, and then from E to C, there is another edge. So whenever there is a concept of directed edge, in that case, the edges can be on both ways, right? Okay. So there goes the directed graph and undirected graph. Now let's look at some, okay, another thing is these edges can have weights. So even in both cases, like this is the first two graphs that we looked at, this one and this one, in these two graphs are unweighted. So the edges don't carry any weight. But here you see this is a weighted undirected graph, right? This is weighted undirected graph. And this one is a weighted directed graph. Now let's look at some practical examples of graphs. So this is a, let's talk about a social network graph. So in social network, you can think every one of you is a node, and the friendship between you is the edge, right? So now you see that, suppose all the students, like whoever is, like every one of you, like including myself, is a node in a social network graph. And suppose I have 100 friends on Facebook. That means I have 100 edges And the question is like, what kind of graph is this? Is this directed or undirected? Obviously, this is undirected because when I am friend with someone, he's also my friend, right? So the friends are not like directional, that I am his friend and he's not my friend. That's not possible, right? So a social network graph is an example of an undirected graph, right? So this is an undirected graph. So say suppose Facebook or any other social network. And this is a graph because anyone can be anyone's friend, right? So that's very much possible that anyone can be anyone's friend. So there is no constraint on the edges. So it's not like a tree. It's not a tree graph. It's just a normal graph because there is no constraint on edges. Any node can be connected, or anyone can be friend with another person. Okay, and then this is an example of a direct. What is a? This is an example of a directed graph. This is a say web site or internet website or web page or internet graph. So the example here is this is a site. Suppose this is your personal site, okay? And then in your personal site, you have a link to your LinkedIn. So this is LinkedIn, say, okay? And then in the LinkedIn, suppose you have LinkedIn has a link to whatever, Microsoft Office or something like that, okay? And suppose this is another page. This is a Bing, right? So I don't know why this is okay. So this is suppose Bing's page. So basically, what you see is this is directed. This is a example of a directed graph because your personal page has a link to LinkedIn, but doesn't necessarily LinkedIn has a link towards your personal page, right? And then LinkedIn has link towards Microsoft Office. So it depends on like on the which direction it has. So every edge here, if you think that every page or every site is a node here, the link from those pages to other pages, or you can think them as edges, right? And these edges actually particularly take you to one direction. And obviously it can be bidirectional. Suppose in your LinkedIn profile, you also put a link to your personal page. In that case, there will be both ways, right? Okay, so, but this is an example. Internet graph is an example of a practical example of a directed graph. And then let's talk about, say, weighted graphs. Okay, so say I'm going to draw some weighted graphs here. So weighted graphs are, say, here in Seattle. I'm in Seattle, and then this is Las Vegas. We can say that there is a link between these two. So say it can be the road link, right? Road link or something. So how many miles are, and the weight can be, and then from Seattle, the road links to Portland, right? And then from Portland, there is link to the Bay Area, San Francisco. So all other things, right? From Portland, there is link to Boise. And each of these road links have a distance. So the distance can be the weight here, right? So I don't know what the distance is, but just making some guesses. So say from Seattle to Portland, there is like 200 miles, something like that. And then from Seattle to Las Vegas, say 600 miles, right? So each of these edges, we can say the cities here are nodes, right? and the road between the cities are the edges, and each of these edges have weight, and weight is a distance. So this is an example of a weighted graph, right? So this is obviously, if you have a road link, this is a undirectional undirectional or undirected graph. But the thing is, what is an example of a directed weighted graph? Just think like this: in big cities, say if you go to Chicago downtown, right? So the streets are like this, and then there are avenues, right? So these are the intersections. You can think these intersections as nodes, and these streets are the link or edges between them, right? Okay. Now, in the downtown, sometimes these roads are, say, one-way roads, right? So if it's one way, then it's like this, right? And each of these roads have they have distance between them. So this is, say, 1 mile or something. This is 2 mile, right? And then in some cases the roads are not directional. So it's not just one way, it's both ways. So in that case, you can say, suppose here, so the road is like, it's a straight roads, but for the purpose of showing it in both directions, I am just drawing curves. So this is an example of a weighted directed graph. The intersections of the roads between the intersections of a downtown. Okay, so let's talk about the properties of a graph. So the properties of a graph are like, as we said, a graph is represented as a set. This is a set of vertices, and this is the set of edges, right? So by this we mean the number of vertices and by this we mean the number of edges. Okay. So then can we just calculate that what is the maximum number of edges that a graph can have? So as we said, there is no constraint in a graph, right? Suppose we think about a graph with 4 edges, and with 4 vertices, where each vertex is connected, has an edge to other vertex, right? So this is the maximum number of edges in this undirected graph. So can we say that if the graph has like n vertices, each vertex can have like n minus 1 edges, right? Can we say that? Because this one, except itself, it can be connected with other n minus 1 vertices, right? So n vertices in total is going to have n into n minus 1 edges divided by 2. The reason is this is an undirected graph. So basically A has edge to C, right? And C also has edge to A, but these two are considered just as one edge. That's why n into n minus 1 over 2. That is the number of edges, maximum number of edges in a undirected graph. But if it was a directed graph, right, in that case, it would have been just n into, so for a directed graph, it would have been n into n minus 1, because each edge can have n minus 1 edges to the other vertices, right? So that's the highest number of edges. So we can say that order of n square. that is the number of edges, right? This is order of n square. If there is like n edges, n vertices, then the number of edges is order of n square. And another thing, you may have a question like, can I have an edge to myself? Yes, that's also, there is no constraint. So you can have an edge to yourself. One example is if you go to a website, right, or web page, if you think the page is a node, in that case, sometimes you are on the home page, but on the top you see the links to other pages, right, to other nodes, and there is one link which says home, right? That means if you click on that, you come back, like you stay on the same page. So that's a self link, okay? So in that case, if you consider that your graph can have a self loop, in that case, it will be n square edges. Okay, so let's talk about dense and sparse graph. Obviously, as the name says, dense graph is where there are like many edges. What is the maximum number of edges we can have? We say like order of n square, right? That is the maximum number of edges. Everything is connected to everything. So this is an example of a dense graph. So you don't necessarily need like all the edges to be dense graph. So even suppose here, I'm not sure if all the edges are connected to each other. Even say for this one, say I give you one example here. You see almost all the edges are connected to each other, but this is not connected to this, right? But it's a dense graph because it has all the edges possible. Whereas the sparse graph is like, as the name suggests, if there are like a few edges, so there are like a lot of other potential edges, but those are not present. Okay, so this is an example of a sparse graph where we don't have many edges. Some other terminologies, we actually need to learn them, because when you are actually solving problem and so learning different graph algorithms, these things will come into the picture. So first of all, path. So path is a sequence of vertices. So it's a sequence of vertices where each adjacent of pair is connected by an edge. So here you see from A to, so this path is like this. This path is A, F, C, D, E, B, H, right? So this is the path here. And as you see that each of the neighboring vertices are actually connected by an edge. So basically a path is, if you can actually from one vertex, if you can go to the other vertex just by traversing the edges, and then it makes a path. Already we know trees, we already like talked about this, like trees is special kind of graph, and we already solved problems for paths in trees, right? Okay, and now let's talk about the simple path. This is an example of a simple path. So path can be simple or not simple. Okay, and then say, okay, sorry. Okay, and then simple path is, this is a simple path, and the other one here you see, this is another graph you see here, A, B, C, B, E. This is also a path, right? Because you see all the adjacent edges actually are connected by all the adjacent vertices are connected by edges. So basically, but the thing is, we are visiting a single vertex B twice. So in that case, it's not a simple path. For a path to become a simple path, none of the vertices should be repeated. Okay, so this is also a path. So this is a path, but this is not a simple path. Okay, so next, cycle in the graph. As we said, like there are no constraints on the edges in a graph. So any vertex can be connected to any other vertex. So obviously there can be cycles, both in undirected graph and directed graph. Okay, so in both cases, you can have like, how, okay. So you see here, right? A cycle means it's the simple definition of a cycle. So if you can just go through the edges and come back to the same vertex, then it's a cycle. So you see here, we have a cycle here, right? And then for a directed graph, to have a cycle, you have to, the same thing, right? You see, we can actually go through all the edges here and then come back to the same vertex. So this is a cycle. Even here you see we can come this way and this is a cycle. Okay, but if you have something like this, say this is a graph, say this is a directed graph between A, B, and C. So here you see that I cannot actually come back to the same node traversing the edges, right? I can go this way and then I'm done. Or even if I go this way, I cannot just fulfill the cycle. So this is not a cycle. So we can say that this graph doesn't have a cycle. And as we know that the trees, right? Trees are undirected graphs, and trees cannot have cycles, right? Because in a tree, every edge defines a parent-child relationship. So if this was a tree, then one of these would have been parent and this would have been child. This is, say, this is parent and this is two's child. But the thing is, you cannot then have an edge between, like, then it becomes ambiguous, right? So tree is an example of a, sorry, acyclic undirected graph. Okay, next is graph representation. This is very important because whenever we will be solving problems, we need to have a graph representation, how graphs are actually represented, right? So far we have talked about like sets of vertices, edges, all abstract things, but now let's talk about how graphs are actually, how can we represent graphs using data structures? So the first way is, we know that this is the, suppose this graph has a vertex set, right? A, B, C, D, and E. And the first way of representing graph is like, and we have to have an edge list of edges, right? Because we know that the graph is represented by the set of vertices and set of edges. Now, how do we represent the edge? Depending on that, there are two ways to represent the graph. So the first way is, this is called adjacency matrix. And this is, as you can see, this is a matrix, and this is not very complicated. You see, for each vertex is represented by a row here, and also the same vertices are represented by a column, right? So the way these adjacency metrics works, so this is a way to represent the edges. So the way it works is, if there is an edge between A to B, then this value is going to be 1. So you see that A has edge to B, C, and D, right? A has edge to B, C, and D. So you see these 3 are 1. Similarly, this is a undirected graph. So if A has an edge to B and C and D, it's also mutual. That means in the opposite direction, B also has edge to A, right? So you can see that B also has edge to A. So A having edge to B means that B also has an edge to A, because this is an undirected graph, right? Okay. And then you see here that D has edge to E, right? So D has edge to E. That means E also has edge to D. You see that? So using the matrix, whenever there is an edge between the vertices, we put a 1. And then if there is no edge, we are putting 0. This is the adjacency matrix representation of the edges. Now, so we are representing the vertices here and here, right? So we are representing the vertices here, and the edges are represented here in the matrix. Now for a directed graph, we can also do this. Obviously, now the change would be like from A to B, there is an edge, right? But that doesn't mean that from B to A, there is an edge. And we do not see anything here, right? You see that? We don't have anything here. So from B to A, there is no edge, but from A to B, there is one. And another important thing you can see here is here D has an edge to itself. So you see that, right? D has an edge to itself. Similarly, in the directed graph, D has an edge to itself. So as you said, like there is no constraint on edges in a graph. So it can have a self loop or self edge. So this is the first way to represent a graph, right? So this is adjacency matrix. Very carefully, just try to remember this, because we'll be using this later a lot. Okay, and the second way is adjacency list. So this is the adjacency list. So here is our graph. And you see the adjacency matrix. So the adjacency matrix representation of this graph is this. But the thing is, most of the graphs in the real world, they are not dense. They are like sparse graphs. Suppose think of social network graph. In a social network, there are like billions of people on the social network, right? So if this is like a social network with billions of nodes, right? Do you think like we have like, how many edges actually we have? Like, it's not possible that someone has billion friends, right? So this person is not connected. There is no one who is connected to everyone, right? So it's not that everyone is connected to everyone. Rather, what happens is only a few people are connected to a lot of people. Say only a few people are there, but in most of the cases, everyone has like maybe out of these billion nodes, it has only 100 friends or 200 friends. So can you think, like, if I want to represent the Facebook graph using an adjacency matrix, what's going to happen is going to have like 1 billion vertices this way, right? And 1 billion this way, and then 0 and 1s. And what's going to happen is most of them are going to be zeros. Do you see? Like there will be only just a few ones, because most of the people out of these billions, everyone is connected to just 100 people, say, on average. So most of these are going to be zeros, right? So we are actually wasting a lot of memory just to store a little bit of information, right? So adjacency matrix is good for a dense graph. But if you have a huge matrix where most of the values are zero, then it's a wastage of memory. In that case, adjacency list is better. What an adjacency list is? So this is an example of an adjacency list. So here we see that it's a list. So each vertex has a list of its neighbors. So you see vertex 1 has a list of 2 and 5. Okay, so it has edges to 2 and 5. And then vertex 2 contains a list of its neighbors 1, 5, 3, 4, right? So 2 has link to 1, right? It has edge to 5, edge to 4, and edge to 3. So this list actually contains all the neighbors of 2. So in total, you see that to capture all the edges, how many spaces we are using? 2 here, and then 4 here, 6, 8, 11, 14, right? So just 14 memory spaces we are using to contain all the edge information. Whereas if I had used a adjacency matrix, I had to use a 5 into 5 adjacency matrix, like 25 spaces, right? Instead of that, just using 14 spaces, I can represent my graph, right? Okay. So using the data structure that already we know, say, we can think, suppose, we already know hash tables, right? So suppose a graph, an adjacency list thing might be each entry. So this is 1. You can think each list is like node information and list of neighbors, right? Suppose for 1, the node information is 1 and the list of neighbors are 2 and 5, right? We can save here like 1, 2, and 5. For 4, the node is 4 and its neighbors are 2, 5, and 3, right? So I can just put it in the hash table 4, 2, 5, and 3. Okay, so there are 2 ways to represent the graph. First is adjacency matrix, and the second way is adjacency list. You can use both, but adjacency matrix is better for dense graphs. But most of the graphs in real world are sparse graphs, which can be efficiently represented using adjacency list. Okay, now there is some benefits of adjacency matrix. Again, it's adjacency list. This is for you. Just note it down. This is for your homework. Just try to Google what is the advantage of adjacency list over adjacency matrix and the vice versa, because both of them have some pros and cons. Obviously, we discussed one. One of them is like for a sparse graph, adjacency matrix takes up a lot of memory, which is just doesn't make any sense. Whereas adjacency list is efficient on memory, but there are other pros for adjacency matrix as well as adjacency list. This is your homework, and please try to study on this or find this by Googling it.